Hello, everyone, and welcome to Nature Nano Talks. I'm Chiara Pastore from Nature Nanotechnology, and I'm really happy to have with me today Professor Kenneth Dawson from University College Dublin. Welcome, and thank you for joining us today, Professor Dawson. So Professor Dawson is well known for his studies on protein corona, of course, and he is with us today to discuss a little bit more about the concept of biological recognition at the nanoscale. He has just published a perspective with us, and so we're very happy to have him with us to chat a bit about this concept and about his views of where the field is going. So to start off, just a very general question, which is really what motivated you to write this perspective?
Okay, well, I mean, we had known almost from the beginning of this game that the nanoscale sort of communications pathways within the cell and between cells and broadly in biology were really special means of transferring complex information. We had seen that through the years in different manifestations. You know, we saw it in vivo, for example, in extracellular vesicles, in cellular synapses, when these things could be sort of looked at well. So we were able to see all of that promise over the years. And it was one of the drivers for us in actually trying to develop sort of nanoscale biology. So that was the sort of original basis. I have to say that it took longer than we expected to really begin to unravel how it worked. And I think there were two reasons that really sort of precipitated the decision to write the perspective now, rather than say a few years ago or a few years in future. The first was a practical reason. This year we're going to see the first kind of corona designs that really do something radically new being published. So we're going to see those nanoparticles covered by an appropriate kind of corona, shall we say, and we're going to be able to see new kinds of things that we haven't seen for 15 years, like gaining access to the cytosol. That's a significant step forward. And so that gave us the confidence to be sure that we're on the right track. So even if we don't have all the answers, we now know certainly that if you find the right corona, you're in and you can do really important things. That's really important. And because it's taking a little bit longer than we expected to unravel how it all works, we thought it was probably a good idea to say this to everybody, because I think it allows people to sort of think of the future and plan forwards.
And so in your perspective, you talk about recognition, bio-nanoscale recognition and identity. And I wonder whether you could explain us a little bit more what you mean by those and what are the challenges in defining these specific concepts.
Here we go. I mean, the first one is a little bit of a cartoon. It's really just sort of highlighting the fact that there's a tendency always to look where all the action is and where there's a lot of light and so forth. So in this field, we've been sort of looking in the darker spot because that's where we think the truth is. So if you look at the bottom right-hand side of the slide, you'll see that there were those two papers in 2012. I sort of explained their context. So they sort of illustrated the fact that particles that entering the cell, the great majority of them, of course, just went to the lysosome, but a very small fraction do interesting things. You'd never notice that unless you had done all of this kind of RAB labeling. And so it was sort of clear that the fundamental question was how to connect what was on the corona to these very rare particles and being able to do something different. And so that has taken us quite a long time to sort of unravel, and that's really what we've been doing. So to come back, in a sense, to your question, what is nanoscale recognition? I think probably the most important thing to recognize is that nanostructures do not present a sort of fixed menu in biology. So when a cell is confronted by a nanostructure, you look at the kind of picture in the upper right, for example, there are all sorts of pieces of information presented at the surface of that nanostructure. And so biology had to develop a very specific kind of interpretive mechanism to figure out what it was going to do with those nanostructures. Now, these are very ancient mechanisms. They're certainly used in things like, some extracellular vesicle processing, some intercellular synapse, and so forth. But the key part of this is that it's really rather different from the sort of on-off kind of switch that you see in a sort of receptor-ligand interaction. That's very simple. That's menu-driven. You kind of know what the ligands. You just choose a ligand from a long list that you know, and you have a receptor that you know. So, but if you look at the picture in upper right, you can see there's no fixed menu. You're going to have to figure out what this nanostructure is, and you're going to have to do it de novo. So bionanoscale recognition, as we see it, is basically that. It is that sort of complex sequence of events, which you kind of see illustrated here. For example, you see some receptors being used to recognize some specific elements. You see the red and the blue lining up, various blues and greens, but then there's lots of other stuff that's going on at that interface at the cell. And then if you look at what's happening underneath the cell, what you're really seeing is all of this machinery, which I can come back to and talk about a little bit more. All of this machinery is being used to process that information to decide what that structure really is. Something that's distinctive about bionanoscale recognition is that it's going to integrate a lot of information from right across that structure. Constitutes a body of very powerful mechanisms, and therefore it's also extremely protected. I think this was something that was not clear in the early years. In the early years, as a community, we find ourselves doing exactly the wrong things to try to access, to be recognized sympathetically in bionanoscale recognition. For example, we used to sort of graft on identical ligands onto particles in the hope that somehow the nanoparticle would sort of take on the characteristics of those proteins. But there's hardly a worse thing that you could do. If you sort of look at the picture that I showed you just a little while ago, nanoscale recognition integrates this whole series of multiple recognitions into this sort of what we call this recognition cluster underneath. And that's fundamentally a danger signal. Normal things do not have, multiply repeated ligands of that type. So the rules are different. If you want to be recognized sympathetically on the nanoscale, you need to speak the language of the nanoscale on the corona. That's fundamentally the picture. You need to understand what patterns, what organizations are necessary for you to send the right signal to say that you're not a danger.
You also talk about the concept, you introduce a new concept, if you want, of Bionano synapse. So how do you picture that? What do you mean by that? And how do you visualize in a way?
Okay, so we use the phrase synapse because fundamentally when the nanostructure is in contact, for example, with the membrane, there's clearly all of this sort of cytosol-facing infrastructure that's being built up. That's clearly being used to recognize this sort of organized structure on the surface of the particle. And so while it is certainly true that there are many physical interactions defining that recognition event, in that sense, you know, it still has biomolecular, sort of specific biomolecular interactions. In some deeper sense, the function of this interface is to communicate information, and a fairly dense set of information too. The information it's really communicating is what this nanostructure is and what should I do about it if I'm in a cell. So over this latency time, what we now see is that there's a sort of a cytosol facing structure that is sort of condensing that information, that's picking up that information from the surface, the corona of the particle. Now, of course, you know, receptor ligand sort of signal transduction and so forth, there are analogies to that, but those tend to be very simple mechanisms compared to what we're discussing here. What we're discussing here is a sort of integration of the whole information, which then has to be embedded in this sort of recognition cluster. That recognition cluster is like the footprint of what has happened up there. That's what I was sort of showing in that upper right panel in the figure. And then based on both the architecture and the molecular identity of that cluster underneath, that's where the decision is held. So in some ways, the recognition cluster is, if you like, the other half of the synapse. The upper half is the sort of tapestry that defines the corona, and the lower half is the footprint that is taken of that. But embedded in that footprint are the sort of decision-making, early decision-making processes about what's going to happen. So there's almost nothing that you can do on the nanoscale that will not be blocked unless you give the right kind of signals based on those organizational principles. Therefore, in some deeper sense, we see this as a synapse. Of course, built on molecular interactions, but a synapse because we think it has a lot of the functionality of a synapse. It's really receiving information, and it's really locally processing that information. The nanoscale environment is so vastly complex, unstructured and unknown. You could never make it work in biology by just knowing the kind of thing it is and having something to recognize it. That could never happen. I mean, you can do that with proteins. You only have 300,000 or something of them. You can just sort of read it off a menu. But if this is unlimited, there's got to be another kind of way of doing this. And this way of doing it has got to be more like face recognition, basically. That's what we're talking about here. It's got to have unstructured information, and it's got to learn how to structure that information inside your cell. That occurs at the nanoscale synapse. It looks like we might have hit it lucky in this respect. There appears, as our current understanding, to be a very significant separation of timescales between this kind of processing machinery and the rest of the things that are happening in the cell. So that's the kind of thing, if you want, is a little bit like the analogy of the hard corona. You can begin to think about it with this separation of timescale and sort of study it in somewhat an isolation. And so that's what has enabled us to kind of pick it out, pick it apart, pull it apart, and have a look at how it's working. And that's really how we're understanding the synapse.
Right. So you basically, how do you think about going about understanding these recognitions? What are the tools besides like the concept of, again, hard corona or soft corona, and playing with that and trying to gather to get some information from that? What are the tools do you have to kind of decode this recognition process and to apply it for?
Yeah, that's the key. That's a key question, and that I would like to stress is where I think the nanoscale community can really contribute on a broader scientific basis. So these questions are not ours alone. These questions are perhaps almost unknowingly in different communities now being studied in depth. I mentioned cell-cell synapses, communications, what's going on there. I mentioned membrane contacts, intracellular membrane contacts. This kind of idea of touch and communicate is becoming a paradigm right across biology. So in that respect, this is the same thing in some sense. However, what's different for the nanoscale community, and where I think we can really make very significant and deep impact on science, is that we control the structures, we make and control the structures that are the objects of our study. Of course, you can study what's happening when a virus interacts with a particle. Of course you can. Of course you can study this sort of intermembrane contacts and so forth. You can do all of that, and we should and are, and maybe we should do it together. But for us, we make these things. And so in our community, so I think, we are able to produce vast bodies of different information on the particle side. We are able to create huge variety of tapestries. We are able to create different shapes that has sort of structures on the nanoscale. We are able to create what has to be read. And this is how we are seeing it at the minute. So we are able to sort of create these different things, and a sort of little bit of a twist of what you might call structure function. Here's the information we created, and now we interpret it on this side. That makes it an awful lot easier because you have so much freedom to vary the information you're communicating. It makes it much easier for us to create this concept of structure, function, information transfer. The other important point I'd like to make is that we've been able to find a few permissive coronas. And not many yet, but a few. And so that means that for the first time, we also have, if you like, the yes story on this side. So we have the answer, yeah, you're okay. In you go, play and do whatever you want. I'm not afraid of you. Coming back to that, I think the tools are always important. Tools are the thing that take a long time. And if I would answer why it has taken so long, I'd say that's part of the problem. Because you're in a field where the tools are not built. So if you're going to make the field, you need to make the tools. Even a much simpler question, which was, as it became clear some years ago, that it was about the organization of the tapestry, it was completely clear you had to map out this. It's completely clear that the spatial organization mattered. It's completely clear that you had to understand this sort of surfacome or whatever you want to call it. But it's surprising how long it takes to really get to be able to map out the surfaces one by one. You find yourself buried in, in sort of constructs, at sort of tied specific locations. You find yourself buried in microfluidics and trying to read them one by one, and that takes a long time, but it's doable. And now many people are doing it, and it's on its way, and I'm not worried about it. Tools on the other side, the challenges are quite different, because the danger is that in the cytosol-facing thing, you're going to disturb it. That anything you do has the possibility to change it, and what you're seeing are reading. Now that's where the separation of timescales thing looks to be helping us. So it seems that we're able to pull it out under very specific circumstances and sort of architecturally sort of unravel it by all sorts of sort of advanced methods where you're sort of looking at proteomics, of architecture rather than proteomics of molecules. You can't get away from imaging tools. I mean, they're clearly central, but you need to put all of this kind of together. Imaging tools, editing tools. You need to be able to edit pieces of that thing out, see what happens. Those sort of ideas. So you're back into advanced molecular biology. You're back into kind of. I think the defining toolkit issue is that you now need to think about architecture on a few hundred nanometer scale. It is not sufficient to know the composition, and other people are doing these things as well in cell biology, as I said, in these different kind of stories. So there's probably going to be an awful lot of interwoven sharing or import export of tools, I would say. But that's the block. There's always, tools take time, and it takes a long time to make them work well.
So to wrap up a little bit, what are your main take-home message? What do you want to readers to take home from your perspective?
So I think I sort of mentioned at the beginning this kind of idea of this cartoon that we became concerned, and part of our community, that a large part of how bionano science and medicine was seen was sort of studying everything under the light, and actually many people knew that the truth lay somewhere else, and that really understanding what these sort of codes were to gain access, understand this machinery, we had to do this, but the money and the action and all that focus was there. And so one thing we wanted to say clearly now, we're not confident that we're on the right track. As I mentioned, we now can see some of this information transfer and read it. We actually have explicit examples which, with appropriate coronas, can do those things that we failed to do for 20 years. So one, to our own community, I would say, which after all, it's important to say something even before you can settle everything. It's important to kind of say, look, we're on the right track now, and let's focus and let's go ahead with this. There is light at the end of the tunnel. I think to a broader scientific community, in answering that question, one cannot be naive. One cannot be unaware of the legacy. And as I said, it became evident in some ways that people were beginning to concatenate the simple idea of putting drugs inside a nano capsule and shooting them in and hoping that something good would happen, that people were beginning to concatenate that activity with what I've been talking about here. In fact, one of the reasons I think for that is that trying to understand what I've been explaining takes a lot of time, and it's hard. And sometimes you don't really know when it's the right time to say, hold up your hand and say, listen, it's going to be okay. Let's look at this carefully, because you need to be really sure of yourself before you do that. And so that other kind of track gained more and more traction, and so it became easy for scientists looking at us in this broader community to think that what we see our science as is something as, putting something in a little nanostructure and shooting it in and hoping that it gets there in drugs. And so we want to say to that audience, a broader audience, look, we are on this right track. There is very substantial science here. If you think about it carefully, it's the same kind of science that you're asking yourselves. Maybe we've bitten off more than we can chew. I mean, I think this is utterly profound, this kind of whole question, and probably it needs others from different communities to help. So that's what we say to the other broader scientific community. We're on the track, join us. The last community, I think, that probably would be an audience would be funders. I think the other thing then, that other thing, take home message that we want to leave with them is, it's hard to say this, but it has to be said, please trust us. We understand, we're not naive, we understand the legacy. We understand how we get here, more deeply perhaps than you can know. But this is a deep and honest scientific exploration. And those of us that are closest to it can see now, we can see very clearly that we can find a way home here. We're not sure how long exactly it's going to take. It depends who collaborates with whom and how it all works. It's going to be a big question. But without the funders of the world pressing the reset button and asking them, you know, allowing this to go forwards in their own jurisdictions. Nobody is asking them that they trust things blindly. There will be more and more structured evidence, and no one is asking that they suspend their judgment. Again, this could be oversold, this platform of ideas. Hopefully not, but it could be. But we are asking for that sort of window of trust to open up again between those of us engaged in this enterprise, the broader scientific community who share our aspirations, and the people who've got to pay for it. And if we can find that triangle of trust again, we're in business. We might still end up doing what others promised on our behalf to do within our generation. That's my opinion. I believe that we can.
Thank you very much, Professor Dawson, for this really, really interesting talk. And thank you for this very optimistic view of where the field can go and of what we can achieve with these this concept in mind. Thank you very much for joining us today, Professor Dawson.
Pleasure.
Bye-bye.
Take care. Bye-bye.